the cosmic web and the structure of the universe. For centuries, astronomy focused on stars and galaxies, discrete points of light scattered across the night sky. But in the late 20th century, a new picture emerged. The universe is not random, but woven into a vast, interconnected structure known as the cosmic web. Galaxies are not isolated islands. They cluster along filaments stretching hundreds of millions of light years, converging at nodes that form massive galaxy clusters. Between these structures lie voids, enormous expanses with few galaxies, spanning tens or even hundreds of millions of light years. This architecture was first hinted at in the 1970s and 1980s, as galaxy redshift surveys began mapping three-dimensional positions of galaxies. The CFA Redshift Survey revealed bubble-like patterns, where galaxies form walls surrounding empty regions. The Sloan Digital Sky Survey later extended this map, tracing filaments and voids across billions of light years. What emerged was not chaos, but pattern. A sponge-like structure with galaxies outlining the invisible scaffolding of dark matter. The cosmic web is more than visually striking. It is the direct imprint of physics. Gravity amplifies primordial fluctuations left by the Big Bang, drawing matter into sheets, filaments, and knots. The scale and geometry of the web test theories of dark matter, dark energy, and cosmic inflation. Studying it is thus not only cartography, but fundamental science, a way to read the universe's history from its largest structures. The origins of the cosmic web lie in the earliest moments of the universe. Inflation, a period of rapid expansion fractions of a second after the Big Bang, stretched tiny quantum fluctuations to cosmic scales. These fluctuations became the seeds of structure, visible today as faint temperature variations in the cosmic microwave background. Over billions of years, gravity amplified these tiny differences. Dark matter, insensitive to radiation, began clustering first, forming the skeleton of halos and filaments. Baryons, ordinary matter, fell into these potential wells after recombination, eventually cooling and forming stars and galaxies. The web is thus fundamentally a dark matter phenomenon, with visible galaxies tracing its invisible scaffolding. Simulations bring this story to life. The Millennium Simulation, Illustris, Eagle, and more recently Illustris TNG and Uchu, model billions of particles representing dark matter and gas. They reveal the emergence of filaments, clusters, and voids from simple initial conditions. These simulations not only match observations, but predict subtle properties: filament thickness, void distributions, and cluster alignments. The agreement between simulation and observation is one of cosmology's triumphs, confirming the lambda CDM model on large scales. Observationally, the cosmic web is mapped in multiple ways. Galaxy redshift surveys like SDSS and DESI provide three-dimensional maps of millions of galaxies, revealing the filamentary structure directly. X-ray telescopes map hot gas in clusters, showing where filaments converge. Gravitational lensing traces the total mass distribution, including dark matter, outlining the web's invisible skeleton. Even the intergalactic medium between galaxies contributes. Quasar spectra reveal the Lyman alpha forest, absorption lines caused by clouds of hydrogen along the line of sight. This forest traces filaments of gas stretching across cosmic distances, providing a unique view of the web at high redshift. New instruments like the Dark Energy Spectroscopic Instrument, DESI, and upcoming missions like Euclid will extend these maps, creating the most detailed, three-dimensional atlases of the universe ever constructed. What emerges is a picture both beautiful and profound. The universe is a web, galaxies like beads on filaments, clusters at intersections, voids in between. The geometry is not random but statistical, with power spectra and correlation functions matching predictions from early universe physics. By mapping the web, we read the universe's DNA. At the intersections of filaments lie the most massive bound structures, galaxy clusters, containing hundreds to thousands of galaxies, trillions of solar masses of dark matter and vast reservoirs of hot gas. Clusters are the engines of the cosmic web. Their gravity lenses light, magnifying distant galaxies. Their hot intracluster medium glows in X-rays and distorts the cosmic microwave background through the Sunyaev-Zeldovich effect. Clusters themselves link into superclusters, forming enormous complexes spanning hundreds of millions of light-years. The Sloan Great Wall, discovered in 2003, stretches 1.4 billion light-years, one of the largest known structures in the universe. Yet even these walls are only part of the web, one strand in a tapestry that extends everywhere. Studying clusters tests cosmology. Their abundance and growth rate depend sensitively on dark matter and dark energy. Observing clusters across time constrains the equation of state of dark energy, making them critical cosmological tools. In this way, the nodes of the web are not only spectacular structures, but precision instruments for physics. Between filaments lie the great voids, vast regions nearly devoid of galaxies. Voids can span 20 to 100 megaparsecs, making them the largest structures in the cosmos by volume. They are not empty, but contain thin wisps of dark matter and faint galaxies. Yet their low densities make them unique laboratories for testing cosmology. Voids are especially sensitive to dark energy and modified gravity. Because gravity is weak within them, any deviations from general relativity manifest more strongly. Their shapes and sizes also test models of cosmic expansion. Surveys mapping voids across billions of light-years thus probe not only structure, but fundamental physics. Philosophically, voids remind us of the universe's vast emptiness. While clusters dazzle with their richness, voids dominate by volume. Most of the universe is not filled with galaxies, but with silence, a sobering reminder that emptiness is the norm, structure the exception. If clusters are the knots of the web and voids the empty spaces, then filaments are the highways that connect it all. These colossal structures stretch for hundreds of millions of light-years, often with widths of tens of megaparsecs. They are not merely chains of galaxies, but rivers of dark matter, gas and plasma. Filaments form as matter collapses, anisotropically. First into sheets, then into filaments, and finally into knots at their intersections. Simulations show that filaments are the first large-scale structures to emerge after recombination, guiding matter toward growing clusters. Galaxies form preferentially along these filaments, funneled by gravity into denser environments. Observations confirm this. Surveys reveal that galaxies within filaments tend to be more massive, form stars differently, and align their spins with the filament's axis. Perhaps the most dramatic proof came in 2019, when astronomers detected the faint X-ray glow of hot gas, threading between clusters in the Able 3391/95 system. This gas, with temperatures of millions of degrees, confirmed what simulations long predicted. Filaments contain the missing baryons of the universe. They are not empty strands of dark matter alone, but vast, hot reservoirs of ordinary matter, invisible until the right instruments revealed them. For years, cosmologists faced a puzzle. The number of baryons, ordinary matter, inferred from the cosmic microwave background, was higher than what telescopes observed in stars and galaxies. Roughly half of the baryons were missing. The solution, it turns out, lies in the filaments. The warm-hot intergalactic medium, WIM, diffuse gas at temperatures of 10 to the power of 5 to 10 to the power of 7 Kelvin, inhabits filaments and sheets. too hot to see in optical light, too diffuse to glow strongly in X-rays. The WIM evaded detection until ultraviolet and X-ray spectroscopy revealed its fingerprints in absorption lines against background quasars. These subtle features, especially of oxygen ions, trace the hidden baryons. Today, astronomers believe that most missing baryons reside in the WHIM. Filaments are thus not only dark matter structures, but baryon reservoirs, accounting for the ordinary matter that galaxies themselves cannot explain. Mapping this diffuse component is an active frontier, requiring sensitive instruments like the upcoming Athena X-ray Observatory. By filling in the census of matter, filaments reveal the hidden bulk of the visible universe. The web is not static, it is dynamic. Galaxies and clusters flow along filaments, drawn by gravity into larger structures. These cosmic flows are measured by peculiar velocities, motions relative to the smooth Hubble expansion. Mapping them reveals the gravitational landscape of the universe. The cosmic flow surveys have charted these motions, showing how galaxies stream toward the Virgo cluster, the Great Attractor, and beyond. The largest coherent motion, known as the dipole repeller and Shapley attractor, demonstrates how both overdense regions and voids shape flows. Galaxies are pulled toward mass concentrations and pushed away from emptiness. These flows confirm the gravitational dominance of dark matter. Without unseen mass, the velocities would be smaller. They also provide cosmological tests. The rate of flows depends on the growth of structure, sensitive to dark energy. In this way, cosmic flows transform the web into a laboratory, where motions of galaxies serve as probes of the universe's invisible components. Numerical simulations are essential for understanding the cosmic web. Starting from initial conditions set by the CMB, they evolve billions of particles under gravity, hydrodynamics, and feedback. The Millennium Simulation, in 2005, with 10 billion particles, was the first to reveal the web's grandeur at large scales. More recent projects like Illustris TNG and UCHU pushed to higher resolution and larger volumes, incorporating realistic galaxy formation physics. These simulations are not only visual marvels but scientific tools. They allow cosmologists to test how dark matter type, dark energy models, and feedback processes shape the web. For example, warm dark matter suppresses small filaments, while self-interacting dark matter rounds halo cores. Modified gravity alters the growth of voids. By comparing simulated webs to observed ones, scientists can constrain fundamental physics. The UCHU simulation, released in 2021, modeled 2.1 trillion particles in a box 9.6 billion light-years across, producing datasets large enough to mimic entire galaxy surveys. Researchers can generate mock catalogues, test survey strategies, and interpret real data. In this sense, simulations are parallel universes, laboratories where hypotheses about the invisible cosmos are played out. The web is not fixed, but evolves. At high redshift, it was more diffuse, with filaments thinner and clusters smaller. As time passed, gravity sharpened the contrasts. Filaments thickened, clusters grew, voids expanded. JWST and ground-based telescopes are now observing galaxies forming along filaments only 1 billion years after the Big Bang, catching the web in its youth. Lyman alpha mapping at high redshift reveals filaments glowing faintly from ultraviolet background radiation. Projects like the Hobby-Eberly Telescope, Dark Energy Experiment, HETDEX, are mapping millions of Lyman alpha emitters, tracing the web at Z approximately 2 to 3, when star formation peaked. Comparing these maps to simulations shows remarkable agreement, yet also reveals surprises. Galaxies often form earlier and brighter than expected, challenging models of baryon physics within filaments. Studying the web across cosmic time is essential. It links the quantum fluctuations of inflation to the distribution of galaxies today. It shows how dark matter, dark energy, and feedback sculpted structure. And it provides a timeline of cosmic architecture, from the diffuse threads of early epochs to the grand tapestry visible now. Voids may seem like empty afterthoughts in the universe's structure, but in cosmology, emptiness can be more revealing than mass. In overdense regions like clusters, gravity is strong and non-linear, making it difficult to isolate small deviations from general relativity. In voids, however, matter density is so low that subtle differences in gravity manifest more clearly. Modified gravity models, such as F of R theories or scalar tensor models, often predict enhanced growth of structure in underdense environments. In such models, screening mechanisms hide deviations in high-density regions but allow them to emerge in voids. Observing how voids expand, how galaxies cluster around their edges, and how lensing distorts their shapes, thus provides precision tests of gravity. Surveys like SDSS and DES have catalogued thousands of voids, measuring their size distributions and lensing signals. The results so far remain consistent with lambda CDM, but uncertainties leave room for surprises. Future surveys like Euclid and Rubin will map voids with exquisite detail, perhaps revealing whether Einstein's theory of gravity is the whole story, or only an approximation. Despite advances, mapping the cosmic web is far from trivial. Galaxies are only tracers, sparse compared to the underlying dark matter. Bias, the fact that galaxies form preferentially in certain environments, complicates interpretation. Observing gas in filaments is even harder, as the WIM is diffuse and faint, requiring long exposures in ultraviolet or X-ray bands. Redshift distortions also complicate three-dimensional maps. Peculiar velocities along filaments stretch structures in redshift space, producing the famous fingers of God effect, where clusters appear elongated. Large-scale infall into filaments creates the opposite, squashing along the line of sight. Correcting these distortions requires careful modeling. Even gravitational lensing, while powerful, faces noise. The intrinsic shapes of galaxies are irregular, and weak lensing signals require averaging over millions. Extracting the subtle lensing pattern of filaments and voids pushes observational limits. Yet each challenge drives innovation, from machine learning algorithms to deeper surveys, steadily refining the cosmic map. The cosmic web is not just a static skeleton of dark matter, but a dynamic ecosystem where baryons flow, cycle, and evolve. Galaxies draw gas from filaments, fueling star formation. Supernovae and active galactic nuclei eject material back into the intergalactic medium, enriching it with metals. Over time, this feedback cycle connects galaxies to the web around them. Simulations like illustrious TNG have traced this baryon cycle in detail. They show that much of the intergalactic medium is enriched with heavy elements carried outward by galactic winds. Observations confirm this. Quasar absorption lines reveal oxygen, carbon, and silicon in filaments far from galaxies, evidence of pollution by stellar processes. The baryon cycle is central to galaxy evolution. Galaxies that remain connected to filaments continue forming stars. Those cut off, perhaps by heating or stripping, quench. The web is thus both environment and fuel line, shaping not only where galaxies form, but how they live and die. One of the most striking features of the cosmic web is its connectivity. Filaments link clusters across vast distances, forming networks reminiscent of biological or neural systems. Indeed, studies comparing the topology of the cosmic web to brain networks have found surprising similarities in connectivity patterns, despite the difference in scales. This connectivity is not coincidence, but physics. The gravitational growth of initial fluctuations produces filamentary networks naturally. The degree of connectivity, how many filaments join at a node, how voids interconnect, encodes information about cosmological parameters. Graph theory and network science are increasingly applied to the cosmic web, treating it as a vast cosmic graph. This perspective has practical implications. By quantifying connectivity, cosmologists can test the impact of dark matter properties, dark energy, and modified gravity. For example, more massive neutrinos reduce connectivity by damping small-scale power. Self-interacting dark matter alters filament thickness. The web's topology is not only aesthetic, but diagnostic, a fingerprint of fundamental physics. The cosmic web exhibits self-similarity across scales. On megaparsec scales, filaments and voids dominate. On kiloparsec scales, galaxies form filament-like patterns of spiral arms and gaseous streams. Even within molecular clouds, filaments of gas-shaped star formation. Some scientists see this as evidence of universal processes. Gravity and turbulence naturally produce filamentary networks, from stars to galaxies to the web itself. This multi-scale perspective links the cosmic web to other sciences. Fluid dynamics, turbulence, and even network theory describe similar patterns. The universe may not only be vast, but patterned, with structures echoing across scales. Such analogies inspire cross-disciplinary work, where techniques from neuroscience or fluid mechanics inform cosmology and vice versa. Philosophically, the recurrence of webs across scales invites reflection. The universe may not be random chaos, but a structured, connected whole. From the synapses in a brain to the filaments of galaxies, networks may be nature's preferred architecture. The ultimate goal of cosmic web studies is a complete map of the universe's structure across space and time. Projects like DESY are gathering spectra of millions of galaxies, building three-dimensional atlases spanning billions of years. Euclid and Roman will extend these maps deeper into the past, while SKA will add hydrogen mapping at high redshift. Such maps will allow not only visualization, but precision measurement. Correlation functions, void statistics, filament thickness distributions, all will test cosmological models. The web will become as familiar a tool for cosmology as the CMB, complementing early universe snapshots with late universe structure. We stand at the dawn of cosmic cartography. The first maps revealed walls and voids. The next will reveal the entire tapestry. Just as ancient explorers mapped Earth's continents and oceans, cosmologists are mapping the universe's filaments and voids, charting a landscape far larger but equally fundamental to human understanding. Galaxies are not randomly oriented within the cosmic web. Observations and simulations increasingly show that their spins and shapes correlate with the filaments that host them. Low-mass spiral galaxies often align their spin axes parallel to filaments, while more massive ellipticals tend to orient perpendicularly. This pattern arises from tidal torques during formation. As matter flows along filaments, galaxies acquire angular momentum from large-scale gravitational interactions. The direction of this torque depends on mass and environment, producing systematic alignments. Such alignments are not just curiosities. They affect weak lensing measurements, as intrinsic galaxy orientations can mimic or contaminate lensing signals. Understanding them is essential for precision cosmology. More profoundly, galaxy alignments show how deeply the cosmic web shapes galaxy evolution. Filaments are not passive scaffolds, but dynamic guides influencing how galaxies spin, grow, and cluster. A galaxy's orientation is thus not merely local, but cosmological, a trace of the web that birthed it. The cosmic web is not only composed of matter and dark matter, but also threaded by magnetic fields. These fields, though weak, often measured in nanogauss, pervade filaments and voids, influencing gas flows and cosmic ray propagation. The origin of cosmic magnetism is still debated. Seed fields may have arisen during inflation or phase transitions in the early universe, later amplified by turbulence and dynamos. Observations of Faraday rotation, where polarized radio waves twist as they pass through magnetic fields, provide the best evidence. The LOFAR and upcoming SKA radio arrays are beginning to map these effects, revealing magnetized filaments stretching millions of light years. Magnetic fields may help explain how gas flows into galaxies, how jets from active galactic nuclei propagate along filaments, and how shocks heat the WIM. The web is thus not only gravitational, but electromagnetic. A plasma network with subtle but significant influence on structure formation. The geometry and evolution of the cosmic web provide critical tests of dark energy. As expansion accelerates, filaments stretch, voids expand, and cluster growth slows. Measuring these changes across cosmic time constrains dark energy's equation of state. Baryon acoustic oscillations, BAO, imprinted as a preferred scale in the web's galaxy distribution, serve as standard rulers. By measuring BAO at different redshifts, cosmologists chart the expansion history. Weak lensing of filaments and voids adds another probe, sensitive to the growth of structure. Together, these methods test whether dark energy is truly constant or evolving. Already, surveys like BOSS and eBOSS have measured BAO with high precision, confirming lambda CDM. But the next generation, DESI, Euclid, Rubin, and Roman, will refine the picture, perhaps revealing subtle deviations. The web is thus not just a structure, but a cosmological tool, its filaments and voids recording the push and pull of dark energy. Beyond shaping galaxy alignments, filaments act as highways, transporting gas and even stars across cosmic scales. Simulations show that galaxies embedded in filaments have higher star formation rates, sustained by continuous inflows of cold gas streaming along filaments. In contrast, galaxies in voids often starve and fade. Observations with instruments like MUSE on the Very Large Telescope have directly imaged Lyman alpha emission from cold gas flowing along filaments into galaxies. These cosmic rivers sustain the growth of galaxies, explaining how they continue forming stars over billions of years. Occasionally, stars are also ejected from clusters or galaxies and travel along filamentary paths, forming intracluster light that illuminates the web faintly. Thus, filaments are not just dark matter spines, but lifelines, feeding galaxies with the fuel of creation. The web is alive with motion, a dynamic circulatory system connecting the cosmos. The cosmic web has invited comparisons to networks in biology, geology, and technology. Neural networks in the brain, vascular systems in plants, river basins, even the internet, all share filamentary, interconnected architectures. Mathematically, they exhibit similar scaling laws and connectivity patterns. This universality suggests that filamentary networks arise naturally when flows optimize efficiency under constraints. In the universe, gravity draws matter into filaments because they are the most efficient paths of collapse. In the brain, neurons form filamentary connections to minimize energy use while maximizing information flow. Nature, from atoms to galaxies, seems to prefer webs. Philosophically, this raises the question of whether the universe's structure is unique or part of a broader principle. that complexity organizes into networks. The cosmic web is thus not only an astrophysical phenomenon, but a case study in universal organization, linking the largest scales to the smallest. As technology advances, cosmic web studies are entering a golden age. Machine learning algorithms now detect filaments and voids automatically in survey data. Fast radio bursts, FRBs, whose dispersion measures track the density of electrons along their paths, are emerging as probes of the web's ionized gas. X-ray and ultraviolet telescopes will map the WHIM more fully. Meanwhile, simulations continue to grow in scale and realism, incorporating not only gravity and gas dynamics, but feedback, magnetism, and cosmic rays. Coupled with massive survey datasets, they will allow precise comparisons and refinements. The dream of a full baryon census, knowing where every atom in the universe resides, is within reach. In the long term, web studies may even extend into multi-messenger astronomy. Gravitational wave sources embedded in filaments could probe their environments. Neutrino observatories may detect signals from structure formation shocks. The cosmic web will no longer be just a visual structure, but a fully characterized physical environment, woven from matter, energy, fields, and forces. The cosmic web stretches across unimaginable scales, and within it lie some of the largest structures known to science. The Sloan Great Wall, discovered in 2003, extends 1.4 billion light-years. The CFA Great Wall, revealed in the 1980s, spans about 500 million light-years. In 2013, the Hercules Corona Borealis Great Wall was identified through gamma-ray bursts, possibly stretching more than 10 billion light-years, making it the largest single structure ever claimed. These vast walls challenge our understanding of cosmic homogeneity. According to the cosmological principle, the universe should be homogeneous and isotropic on scales larger than approximately 300 million light-years. Yet these walls seem to extend much farther, raising debates about whether they are genuine structures or statistical anomalies. If confirmed, they may point to new physics or at least to more complex interpretations of cosmic isotropy. At the very least, they show that the cosmic web is not just aesthetically complex, but staggeringly vast, pushing the limits of what structure means on universal scales. The cosmological principle assumes isotropy. The universe looks the same in all directions. Yet mapping the cosmic web inevitably raises the question, is it truly isotropic? While the cosmic microwave background is nearly uniform, large-scale structures sometimes appear lopsided. Some analyses of galaxy surveys suggest hints of hemispherical asymmetry, where one half of the sky contains slightly more structure than the other. The distribution of quasars and gamma-ray bursts has also sparked debate about anisotropy at very large scales. Are these statistical flukes, survey biases, or genuine signals of new physics? The cosmic web is key to resolving this. By mapping filaments, voids, and walls across the full sky, future surveys like Euclid and SKA will test isotropy with high precision. If anisotropy exists, it could signal that inflation was not perfectly uniform, or that exotic physics shaped the early universe. For now, the principle holds, but the web continues to push its limits. The cosmic web is not only a product of gravity, but also a fossil record of the universe's first moments. Inflation, the rapid expansion thought to have occurred in the first 10 to the negative 35th seconds, left imprints in the form of density fluctuations. These fluctuations seeded the filaments and voids we see today. The statistical properties of the web, its correlation functions, power spectrum, and topology, reflect those initial fluctuations. The near-Gaussian distribution of structures matches inflationary predictions. Small deviations from Gaussianity are actively sought, as they could distinguish between inflation models. Baryon acoustic oscillations, BAO, also serve as direct fossils of early sound waves in the plasma, imprinted as a preferred clustering scale in the web. Their measurement in galaxy surveys is one of the strongest confirmations of the inflationary paradigm. In this sense, every filament and void is a time capsule, carrying information from the universe's birth to its present architecture. On the largest scales, the cosmic web follows linear growth predicted by cosmological perturbation theory. But on smaller scales, non-linearity dominates. Galaxies, feedback from supernovae and black hole activity inject turbulence, heating, and shocks into filaments. The neat skeleton of dark matter becomes entangled with baryonic physics. This complexity is both a challenge and an opportunity. It makes modeling more difficult, as baryonic processes introduce uncertainties. Yet it also enriches the web, linking cosmic structure to galaxy formation and evolution. Understanding when and how the linear web gives way to nonlinear complexity is one of the central goals of modern simulations. In this sense, the cosmic web is not static scaffolding, but a living system. Its filaments thickening, its voids evolving, and its clusters boiling with feedback. The elegance of large-scale structure is married to the messiness of astrophysics, producing a universe that is both ordered and chaotic. The cosmic web is a laboratory for physics across scales. On scales of hundreds of millions of light-years, it tests dark energy and the cosmological principle. On cluster scales, it probes dark matter through lensing and hot gas. On galactic scales, it reveals baryon cycling, star formation, and feedback. Even smaller scales connect back to the web. Cold gas streams along filaments into galaxies, regulating their star formation histories. The alignment of galaxies with filaments links angular momentum generation to cosmic flows. The temperature and ionization state of the WHIM informs feedback models. Thus, the web is not merely background, but context. It integrates phenomena across orders of magnitude, from quantum fluctuations stretched by inflation to the spins of galaxies. To study the web is to study the universe as an interconnected whole, where no scale is isolated from another. Perhaps the most profound aspect of the cosmic web is existential. We live inside it. Our Milky Way is part of the Laniakea supercluster, a vast basin of attraction defined by cosmic flows. Matter, from millions of galaxies, flows along filaments into this region, converging toward the great attractor. Our position in the cosmic web is not arbitrary. We are bound to its strands, drawn by its flows, and destined to follow its currents. This perspective reshapes how we think about location in the universe. We are not in an isolated galaxy, but inside a filament of a vast web, one node among billions. Just as a neuron is part of a brain, the Milky Way is part of a cosmic network. To see ourselves this way is to accept that our cosmic identity is collective, embedded in a structure far larger than we can imagine. The discovery of the cosmic web has sparked philosophical reflection. Cultures have long used the metaphor of webs and nets to describe reality. Indra's net in Hindu and Buddhist cosmology, the web of fate in Norse mythology, the interconnectedness of being in indigenous traditions. Now science provides literal confirmation. The universe is indeed a web. This metaphor bridges science and philosophy. The cosmic web shows that connection, not isolation, defines reality. Galaxies, like human societies, are not separate but linked by flows, interactions, and shared origins. The universe itself may be understood as a network of relationships, both physical and metaphysical. For cosmologists, this philosophical resonance enriches the science. The cosmic web is not only a data set but a symbol, uniting mathematics, physics, and meaning. It reminds us that the pursuit of knowledge is also the pursuit of perspective, of seeing our place in the grander weave of existence. The study of the cosmic web is still young. Future surveys will map billions of galaxies, measure weak lensing across the sky, detect the WIM in detail, and trace cosmic flows to greater depths. Machine learning will refine void and filament catalogues. Multi-messenger astronomy will embed gravitational waves and neutrinos into the web's framework. As precision grows, the cosmic web will move from visualization to diagnosis, becoming a tool for testing fundamental physics. Dark energy models, dark matter interactions, neutrino masses, and inflationary physics will all be constrained by Webb statistics. By mid-century, Webb cosmology may rival the cosmic microwave background as the primary testbed of cosmology. And beyond measurement, the Webb will inspire. Its patterns echo across scales, from neurons to rivers, from social networks to galaxies. Its discovery confirms what poets and philosophers have long suspected, that reality is woven. To live in such a universe is to be part of a vast, interconnected whole, where the story of galaxies and the story of humanity are threads in the same fabric. Among the most elusive actors influencing the cosmic web are neutrinos. These ghostly particles with tiny but non-zero masses free stream across the cosmos at nearly the speed of light. Because they move so quickly, they suppress the growth of structure on small scales, smoothing out density fluctuations. The effect is subtle but measurable. Cosmological simulations that include neutrinos show that filaments become slightly less pronounced, voids slightly rounder, and small galaxies slightly rarer. Galaxy surveys and weak lensing maps are now sensitive enough to detect these differences. Indeed, combining Planck CMB data with large-scale structure surveys places strong limits on the total neutrino mass, currently less than 0.12 electron volts. This means that the web itself is a neutrino detector. A vast three-dimensional laboratory, recording the imprint of these faintest particles. By measuring the fine structure of filaments and voids, cosmologists can constrain fundamental particle properties. The interplay between microphysics and megastructures is nowhere clearer. The lightest known particles help shape the largest known structures. If the web is the skeleton of the universe, tomography is how we X-ray it. By combining redshift surveys, weak lensing, and absorption line studies, astronomers can reconstruct three-dimensional maps of the web across cosmic time. The Lyman alpha forest in quasar spectra provides one method. Each quasar acts as a flashlight, its light absorbed by hydrogen clouds along the line of sight. By combining many such lines of sight, one can reconstruct a three-dimensional map of gas distribution at high redshift. This technique, pioneered by surveys like BOSS, reveals the web as it appeared billions of years ago. More recently, fast radio bursts, FRBS, have emerged as new probes. The dispersion of their pulses measures the electron density along their path, providing integral constraints on the web's ionized gas. With hundreds of FRBs now detected and thousands expected with SKA, web tomography will expand rapidly. Ultimately, the goal is cosmic web cartography. Dynamic, multi-epoch, three-dimensional maps showing how filaments, voids, and clusters evolved. Such maps will allow direct comparison to simulations, pinning down dark matter properties, neutrino masses, and dark energy dynamics. While dark matter defines the web, galaxies provide its most visible traces. Their distribution along filaments, their clustering around nodes, and their absence in voids all outline the underlying structure. But galaxies do more than trace. They interact with the web itself. Galaxies embedded in filaments show higher rates of star formation than those in isolation, likely due to steady gas inflows. Their morphologies reflect filamentary alignments. Cluster galaxies at web nodes experience RAM pressure stripping and mergers, shaping their evolution. In voids, galaxies tend to be small, blue and irregular, reflecting isolation. Thus, the web is not merely scaffolding, but environment, shaping galaxy growth and character. Our own Milky Way resides in a filament of the Laniakea supercluster, influenced by flows toward the Great Attractor. Even our galaxy's evolution is inseparable from the web around it. At first glance, the cosmic web seems remote from the question of life. Yet its influence is profound. Without dark matter filaments, galaxies would not have formed in time to create stars and planets. Without voids, cosmic flows would be different, altering star formation histories. The web sets the stage for the emergence of habitable worlds. Some anthropic arguments even suggest that the web's scale and structure are necessary for life. If dark matter density were higher, structure would collapse too quickly. If lower, galaxies would not form. If dark energy were stronger, filaments would never have thickened. The balance that produced the web is the same balance that produced us. In this sense, the cosmic web is not only astrophysical, but existential. Its strands are the arteries of creation, channeling matter into galaxies, stars, and eventually biology. To understand the web is to understand one of the deepest preconditions for life itself. Like all structures, the web evolves and will one day fade. Dark energy's acceleration ensures that distant filaments and clusters will recede beyond our cosmic horizon. In trillions of years, only the local group and its merger remnant will remain visible. The vast filaments that now connect us to Virgo, Perseus Pisces and Shapley will slip away into invisibility. Even within the horizon, the web will thin. Clusters will merge into isolated islands. Voids will expand, and filaments will stretch. The cosmic web is transient on the longest timescales, a temporary phase between the hot plasma of the early universe and the cold emptiness of the far future. This perspective lends poignancy to cosmic cartography. We live at the only epoch when the web can be fully mapped, when galaxies still shine and filaments still connect. Future civilizations may never know the web existed. Our era is privileged, perched between creation and dissolution, able to witness the universe's grand design. The web is more than physics. It is metaphor. Across cultures, webs symbolize connection, interdependence, and fate. The Norse spoke of the Norns weaving destiny. Buddhists envisioned Indra's net, each jewel reflecting all others. Native American traditions saw spider webs as symbols of creation. Now modern science confirms that the universe itself is woven. This metaphor resonates with human experience. Just as galaxies are linked by filaments, so are people linked by relationships, societies by networks, ecosystems by flows. The cosmic web reflects a universal truth. Reality is not isolation, but interconnection. To live is to be part of a web, whether biological, social, or cosmic. For science, the metaphor serves as inspiration. The web encourages interdisciplinary thinking, drawing analogies between cosmology, biology, neuroscience, and information theory. It reminds us that patterns repeat across scales, that nature prefers networks, and that our place in the cosmos is part of a larger fabric of being. The study of the cosmic web integrates multiple threads of cosmology. Dark matter as scaffolding, dark energy as shaper of expansion, baryons as tracers, neutrinos as smoothers, magnetism as subtle influence. It unites simulations with observations, theory with philosophy. As precision increases, the web will become the primary testing ground for new physics. Does dark matter self-interact? Does dark energy evolve? Are neutrinos heavier than we think? Is gravity modified on large scales? Each question will be tested by the web's geometry, connectivity, and evolution. But beyond physics, the web provides a worldview. It shows that the universe is structured, not chaotic, connected, not random. It situates us within a network stretching billions of light years, linking our galaxy to others, in flows of matter and energy. It reveals that the same gravity binding apples to Earth shapes the filaments of the cosmos. The cosmic web is the universe's grand architecture. Born of quantum fluctuations, sculpted by gravity, traced by galaxies, and revealed by surveys, it is the largest structure ever discovered. Its filaments carry gas to galaxies, its voids test gravity, its clusters anchor the cosmos. It is not only beautiful, but essential, the backbone of creation. We are part of this web. The Milky Way lies within a filament of Laniakea, pulled by flows into larger structures, destined to merge, evolve, and eventually fade. Our place is not at the center, but within a strand, one node among billions. Yet from this strand, we can perceive the whole, mapping the weave of reality itself. Chapter 4 closes with this recognition: the universe is a web. It is woven from matter and energy, from dark and light, from seen and unseen. To study it is to glimpse the pattern of existence, a tapestry stretching from the smallest quantum fluctuations to the largest superclusters. The cosmic web is not merely structure. It is the story of the universe written in threads.